Nature is governed by four known fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity governs the motion of planets and stars, while electromagnetism controls atomic and molecular interactions. The strong force binds atomic nuclei, and the weak force governs certain types of radioactive decay. For decades, scientists have speculated about a fifth force that could explain phenomena not fully accounted for by these forces, such as dark matter, dark energy, or anomalies in particle interactions. The Pioneer anomaly, where spacecraft exhibited unexpected deviations in their trajectories, spurred interest in whether an unknown force might be at play. So, there's a force that is, if the four known forces are the pillars holding up the universe, a fifth force would be like an unseen thread subtly weaving through the structure, altering its behavior in ways yet to be understood. A fifth force could take many forms, such as a long-range interaction that slightly modifies gravity, or a short-range force acting only over microscopic distances. It might arise from a new particle or field, similar to how the photon mediates electromagnetism. Theoretical candidates include interactions linked to dark energy, which accelerates the universe's expansion, or scalar fields hypothesized in extensions of general relativity and quantum mechanics. Detecting this force would require identifying its mediator, often referred to as a fifth force particle. Experiments with ultrasensitive torsion balances have searched for deviations from Newtonian gravity at small scales, which could hint at a fifth force. A fifth force would be like discovering a hidden ingredient in a recipe, present but subtly influencing the final outcome in ways we hadn't noticed before. Over the years, several anomalies have suggested the possibility of a fifth force. For instance, variations in gravitational measurements near certain materials led to speculation about a composition-dependent force. Studies of particle decay rates have occasionally revealed unexpected discrepancies that could point to new interactions. While many of these anomalies are eventually explained by experimental errors or known physics, they continue to inspire investigations into hidden forces. The fifth force hypothesis gained traction in the 1980s when researchers observed small deviations in gravitational forces between objects of different compositions, leading to intense experimental scrutiny. Anomalies in known forces are like ripples in a calm pond, suggesting unseen disturbances below the surface. Dark matter and dark energy are two of the biggest mysteries in physics, comprising about 95% of the universe's mass energy content. Neither interacts directly with light or known particles in conventional ways. A fifth force could potentially explain these phenomena by introducing new types of interactions or particles that influence the large-scale structure and dynamics of the universe. For instance, some theories propose that dark energy arises from a scalar field associated with a fifth force. The accelerating expansion of the universe attributed to dark energy might be driven by a previously undetected force permeating space. Dark matter and dark energy are like shadows in a room. You can see their effects, but the source of the shadow remains elusive. Searching for a fifth force involves highly sensitive experiments designed to detect deviations from known physical laws. Techniques include torsion balance experiments to measure tiny changes in gravitational attraction, atom interferometry to test the equivalence principle, and particle physics experiments at colliders to search for new mediating particles. These experiments often focus on extreme environments such as high-energy collisions, deep underground laboratories, or cosmic observations, where subtle effects might become apparent. The Large Hadron Collider, LHC, has conducted experiments to detect new particles or forces beyond the standard model, such as hypothetical dark photons that could mediate a fifth force. Detecting the fifth force is like listening for a faint whisper in a noisy room. It requires the most precise instruments and carefully controlled conditions. Think about proving the existence of a fifth force is challenging due to the need to distinguish it from effects caused by the known forces. Many experimental anomalies that initially hint at new interactions are later explained by errors, systematic noise, or overlooked variables. Additionally, the fifth force may manifest only under specific conditions, such as extremely small distances, high energies, or near massive celestial objects, making it difficult to observe. Efforts to measure deviations in gravitational force at microscopic scales require isolating experiments from seismic, thermal, and electromagnetic disturbances. Finding the fifth force is like searching for a needle in a haystack, where the haystack itself is constantly shifting. Discovering a fifth force would revolutionize our understanding of the universe, requiring a reworking of the standard model of particle physics and potentially Einstein's general relativity. It could provide insights into unifying the known forces, solving the mystery of dark energy, or uncovering new dimensions of space and time. Such a discovery might also pave the way for advanced technologies, including novel methods of energy manipulation or communication. The power of the world, now in retrospect, solving the mystery of dark energy manipulation. Unifying gravity with quantum mechanics through a fifth force might provide the long-sought theory of everything, linking all known physical phenomena. A fifth force would be like finding a missing puzzle piece that connects seemingly unrelated parts of the universe's grand design. Several theoretical models propose mechanisms for a fifth force. Scalar tensor theories extend general relativity to include additional fields, potentially explaining dark energy. Other models introduce new particles like dark photons or axions that could mediate unknown interactions. Some proposals suggest that the fifth force could vary with distance or composition, unlike the constant nature of gravity or electromagnetism. There's so many theories I could go on forever. Chameleon fields, a theoretical concept, propose a force that changes its strength depending on the local density of matter, making it hard to detect in everyday environments. Theoretical models of a fifth force are like blueprints for invisible bridges, conceptual frameworks connecting unexplored territories of physics. As technology advances, so does our ability to probe the universe for hidden forces. Upcoming experiments, such as more powerful particle colliders, next-generation gravitational wave detectors, and satellite-based measurements of cosmic phenomena, promise to push the boundaries of detection. These efforts could either confirm the fifth force's existence or rule out many of the current theories, refining our understanding of fundamental physics. The proposed Einstein telescope, a future gravitational wave observatory, could detect subtle deviations caused by a fifth force near black holes or neutron stars. Exploring the fifth force is like charting the edges of a map. Each discovery extends the boundaries of our knowledge and opens new frontiers for exploration. The search for a fifth fundamental force represents one of the most exciting frontiers in physics. Whether it remains an elusive mystery or reveals itself through cutting-edge experiments, The pursuit pushes the limits of our understanding of the universe. Such a discovery would not only answer fundamental questions, but also revolutionize technology and redefine our place in the cosmos.